Okay, hello everybody. I think they're all slowly coming in now. Welcome to the latest episode of the Material Science Pioneers in Art and Archaeology webinar series. My name is Celia Chari, and I'm going to be the host for today's talk. I'm really excited to introduce our speaker, Dr. Marco Nicola. Before I do, I have a few announcements about the webinar that I'd like to share with the audience. First, I'd like to let our audience know that the way that the American Ceramics Society organizes webinars is moving towards a different direction. So starting from October of this year, it is possible that our webinar will no longer be free to register for non-members. So if you are not a member of the American Ceramics Society, this might be applicable to you. If you are a member of ACerS, registration will continue to be free for you. If you're not a member, there may be a small fee applied to register for future webinars. But I do want to emphasize that this is only going to happen from October onwards. So the webinar that is scheduled for September will not be affected by this transition. The details behind this change are still being evaluated, so I would like to invite you to fill out a survey that I'm going to link below so that your voice can be heard as we decide on future directions for this series. And I'm just going to type it here and post it for those of you. Oh, that's just for hosts and panelists. Let me do it now. For those of you who would like to fill it out. And it's also just in general to hear your thoughts about your thoughts on the webinar and present and past talks. So with this news, if you are interested in becoming a member of the American Ceramics Society, there are two different types of memberships that I want to mention. If you are a graduate student or pursuing either a master's or a PhD, there is the possibility for the Art, Archaeology, and Conservation Science Division to waive your membership fee for 1 year. I will write down all the information in the chat for you to fill out the forms and send them over to me or Vicki Evans. And secondly, if you are new to the American Ceramics Society, so if you've never been a member before, it is possible for you to get a complimentary 1-year membership. So for your first year, it would be free of charge. And going back to the previous announcement about potential fees for the webinar, this is something that you may consider just for testing out what it's like to be a member of the American Ceramics Society and the benefits that it can bring you. So I'll fill out that information in the chat for you to look at it more carefully as you make that decision. And the last thing is just to remind everybody that previous webinars, including the current webinar that's going to be recorded, will be posted in the ACerS YouTube page so that you can view it in the future. Okay, so with that housekeeping out of the way, I'd like to introduce our speaker. Dr. Nicola is a research fellow at the University of Turin, where he earned his PhD in chemical and material sciences, exploring the ancient origins of Egyptian blue and its potential modern and future applications. His research is characterized by an interdisciplinary approach that combines chemistry, material science, history, and conservation, aiming to develop innovative solutions for the protection of artistic heritage, and also for technologies of tomorrow. Today, he will be talking about his work on the renaissance of Egyptian blue and related 2D silicates. I was chatting to Dr. Nicola before this webinar, and from everything that I've heard, he is the person for Egyptian blue, so I'm really excited to hear his talk. And Dr. Nicola, please take it away.
Thank you, Celia, for this introduction. And I quickly go to the matter because there is a lot of things to say. And so, first of all, I want to start from the from the very beginning. So the fact that we observe the planet as a blue planet. But we have seen this also very recently by the Artemis mission, and so one can wonder that or infer that blue things on the Earth would be very easy to find, but instead that is not the case. Blue is a rare color. Is not present normally in soils, in rocks. It's very seldom found in any geological deposit. And for this reason, for many thousands of years, people didn't use blue at all. And so we observe the paintings from, for instance, 45,000 years ago that are made with red and maybe black and maybe some earth pigments that are those one on figure 1. And that are the most common color of the soil. And if we remove the sea from the planet, all the surface would be of those colors, but not blue. And so when something is rare, immediately human take it as something that is special, that is sacred, that is magic. And so blue always attracted the imagination of man. And even if it was very, very rare and almost useless in a certain way. So this story, for instance, starts when people develop new word. So when people develop, when a population develop a new word to refer to something, it's because it's useful. And we know that each civilization, each people, each village that made a new language always invented, first of all, a word for the concept of white or black, and then for red, and then for green or yellow. But blue arrived very late and is so rare on the surface of the earth that even the word they used is not a concept of blue, but is a material. It's very common, this process in linguistic way. For instance, we use it for gold. When we want to say something is the color of gold, we use the term gold, that is a material. And those material that stood for the concept of blue was lapislazuli. Lapislazuli was the term currently used in ancient time to refer to a blue thing. So when I want to say something was blue, I have to say something is lapislazuli. And this stone became very not popular because was the only blue stone. And so, but very rare, very expensive, and very, so there was a kind of rush to go and search and found it and exploit it. But the only known quarry was on those Hindu Kush pass. It is a very difficult place to reach with narrow valleys and very difficult passage to go into civilized places. But from the very beginning of the human civilization, they started to take those material and export all over the ancient world in the trade routes that at a certain point would be the Silk Road. But at that point were spread trade route that arrived from the very deep part of Asia to the Mediterranean as well as to China. Obviously, in the Mediterranean, they arrived, for instance, in Babylon, and so we can observe the standard of ure, for instance, but also in Egypt, where it was very priced, and for instance, Tutankhamun had all his mask carved and filled with inlays of lapis lazuli. At that point, in Egypt, many thousands of years before Tutankhamun, they understood that those material is is very interesting also to be produced, since it can be a source of income very important. And so they they find a way to produce a blue material that was similar to lapis lazuli, and they understood its potential. And we don't know exactly how they call it, because it was before the first dynasty, so more than 5,000 years ago. And an American scientist, Corcoran, found it in Boston, the first example known of the use of Egyptian blue in pre-dynastic period, so before the first dynasty. And then they developed it, obviously, in Egypt, and they call it simply Hasebet irit, that means artificial lapis lazuli, obviously. And even if the composition is very different, they developed it how? Simply by developing the copper technology. So we are in the Bronze Age. And so in Bronze Age, they start to use bronze ores, so copper ores, to make bronze. And so in this moment, they were able to use some new material like copper carbonate, or maybe some copper scrap that was something that stay after the alloying, after the production of other items. There was some vast of rich in copper. So they use it probably with some sand, so with a technology that is similar to the pottery. So it is a mixture of pottery and metallurgy, and they mix all those raw materials that are common for both of those technologies, and found that it's possible to produce a deep blue material, very expensive and with a great potential. And they started to produce a material that was produced then for many thousand years and exported all over the Mediterranean and West Asia. It never arrived in East Asia or in very deep Northern Europe, and in South Sahara, but all other parts of the world were full of Egyptian blue. Those material, by the way, is a very strange material. We understood this thing very early, so very late, and only at the beginning of the 21st century, so only about 20 years ago, 30 years ago, we understood that it is luminescent, and it make it possible to make this photo, for instance. This photo is the luminescence of Egyptian blue that make it possible to highlight its presence. Thanks to this property that is very rare, there are very few material, really almost no material that has these features. So to be luminescent into the infrared region when they are enlightened by visible light. So when they are stricken by visible light, they become luminescent in the infrared region. And only very few material do that. One important material that do a similar thing is ruby, but ruby need the UV light to be luminescent in the infrared region. Instead, Egyptian blue can do that only using visible light. And so it's very strange. We understood this, and it opened a new paradigm of technology, but we will see it later. Ancient Egypt observed the production of many things made with Egyptian blue. First of all, we have to understand that Egyptian blue is not simply a pigment. Is a so-called vitreous material. So archaeologists call it a vitreous material. To be honest, it's not a vitreous material. Now we will see it. Is a glass ceramic material, to be more specific. But anyway, we can produce it in a sort of blocks of Egyptian blue that can be produced and carved, or can be shaped and then fired, and so to obtain object made of Egyptian blue, a material. Then if I crush that material, I can produce also a pigment that I can use to paint, for instance, sarcophagus. But the way I use to produce Egyptian blue can deeply change its nature and its features. In the ancient time, they used a melt flux method to produce Egyptian blue. So they take sand that basically is made with silica and calcium carbonate. So probably they already know where a sand is right with the right ratio of calcium carbonate and silica. So they know where to source this kind of sand, and then mix copper containing material and the flux that is that is something that contains sodium or potassium. Obviously, it is also possible that they put silica, a source of calcium, like lime, for instance, a source of copper, and a flux that is normally with potassium or sodium. So we have those two possibilities. Probably there was also different in time. So maybe at the very beginning they used the flux that are mainly based on potassium, that are maybe from ashes. And then when glass technology arrived, 2000 later, in comparison with Egyptian blue, they start to use sodium containing flux like natron. Natron is a very important material for those applications, and was a key material for many thousand years for the production of Egyptian blue. Anyway, the way that I use to produce Egyptian blue can deeply change its nature, its luminescence, its features. And we, for instance, here, we can compare the production of Egyptian blue made with two different techniques. One is melt flux synthesis, that is a traditional method that is very similar to those used by Egyptian. And another is solid state synthesis. That is a method that didn't imply the use of flux, but need a higher temperature, not very higher, like 100 degree more, so not 900, but 1000 degree you need to produce this kind of Egyptian blue. And the features different, which are the color is very different. So the melt flux method produce Egyptian blue deeper in color. Instead, solid state produce a pale Egyptian blue. And the structure of the grain is very different, because in flux method, you have a crystal of Egyptian blue in a matrix that is made of glass, of copper-rich glass. Instead, in solid state, you have grain of silica surrounded by cuprorivaite, that is the main component of Egyptian blue, the one that is luminescent. So this is the possibility with two-stride method of production. With another method of production, we can avoid the presence of a bulk silica core into each grain of Egyptian blue, and we can improve dramatically the luminescence of the material because we have pure cuprorivaite, that is the active crystal into Egyptian blue, so the one that is luminescent, without the glass matrix. The glass matrix is instead absorbing the luminescence, so is kind of self-absorbing material. So if I can avoid the production of glass, I can improve the luminescence, and this is one of the work, for instance, that we have made, making Egyptian blue that is three times more luminescent than commercial Egyptian blue, that is this one with K120 and K10 are two commercial samples of Egyptian blue, and the new synthesis made it possible to make Egyptian blue that is 3 times more luminescent, but we can arrive also to 5 times more luminescent, and we are improving and improving. Obviously, we can also try with other kind of synthesis, so not based on solid state, but based on other philosophies. And in this American Ceramic Society, for sure you have a lot of idea about those kind of new paths that can give Egyptian blue with higher features. So this is an idea. But if we go into the structure of the single crystal of cuprorivaite, so this active material inside Egyptian blue, we can we can observe its inner structure. First of all, the plain formula of cuprorivaite is a tetrasilicate of calcium and copper. So there is 1 calcium, 1 copper, 4 silicon, and 10 oxygen. And they organize themselves in a layered pattern. So you have a layered structure that is almost two-dimensional because it's corrugated. So it's not two-dimensional like graphene, but it's quite so like graphite, but it's quite two-dimensional. It's almost two-dimensional. And so we have a layered material that we see you can exfoliate in nanosheet and obtain quasi two-dimensional particles. The corrugation so it is depicted in this picture. So the layer is not hexagonal like the one in graphene, but is octagonal and square. That then corrugated give the specific structure of the single layer of cuprorivaite. Stability. This pigment is very, very stable. So it is luminescent after thousands of years. So these features to be luminescent is possible to observe even after thousands of years. Obviously, sometimes some change in color is observed, but normally is not due to the alteration of the structure of Egyptian blue, but to the alteration of the surrounding material. So maybe the binding media that are organic material change their color, and so the general appearance of Egyptian blue can change in tone, and so we can observe a blackening or the turning it green, or that are the most common alteration. But by itself, the material is very, very stable. And also those change probably affect not the cuprorivaite, but the glass matrix more than cuprorivaite. So it is a very, very stable material. It can hold with very acidic environment like concentrated hydrochloric acid, or very basic environment like concentrated sodium hydroxide. and you can have almost no variation in Egyptian blue. And also you can go with a strong oxidizing environment, or also strong reducing environment, or you can have light, you can have many kind of stress, and Egyptian blue almost stay as it is. So this is a great opportunity, since this silicate material is very stable, and so is very safe also, because it don't release into the environment any kind of maybe possibly dangerous material, even if here the most dangerous can be only the copper, because the other are very common and widespread material in the environment. After the conquest of Egypt by the Romans, the production of Egyptian blue became something that is very popular, and so it's kind of ancient time Egyptomania that almost is at the same time of the conquest of Egypt. At the time, Vitruvius wrote his famous book about Egyptian blue production, and Egyptian blue was present in Italy. Also, Etruscan use it. Also, Greek in the south part of Italy use Egyptian blue. Also in Greece and many other parts of the Mediterranean. But the advent of Rome put it as a material that is a kind of status symbol and standard all around the ancient Roman Empire. This room, for instance, that we discovered, that has been discovered in 2024 in Pompeii, was full covered of Egyptian blue. And we studied it. We also understood how much Egyptian blue was present, and was a very rich family. And we understand also how much it has been the price of those Egyptian blue. This is a very recent paper we have just published, if you want to discover all those information. So with the Roman expansion, Egyptian blue reached all parts of Europe and many other parts surrounding the Mediterranean. And also it go beyond Roman possession, for instance, in Persia, and in other parts. For instance, also it was found in Norway, but by trade. Instead, in Persia, it's possibly that it was produced also. But at a certain point, during Middle Ages, Egyptian blue mysteriously disappeared. And this is a mystery that was my first quest during my PhD. So why Egyptian blue stopped to be used, and how it was possible it was not more used. So there are many theories about this. One is that neutron, so the main flux used to produce Egyptian blue, but also to produce glass and to make many other things, was a kind of scarce material. And why it becomes scarce? Probably due to a Little Ice Age. So the late Antiquity Little Ice Age that start in the 7th centuries, in the 6th century, and as is speaking 7th and 8th century, probably had some effect also on those neutron production. This is not my idea, is an idea that is by Shorten and other. And the idea is that, my idea is that those neutron lack also force the abandon of Egyptian blue. But there is a small village in Italy where there is a church of the wrong period. So when in theory there would not be possible to have Egyptian blue because there was no neutron, that is full of Egyptian blue. So how they can have this opportunity to produce a fresco full of Egyptian blue when Egyptian blue was no more available. And so we made those study, and we understood that probably they used another flux that is zinc, probably from brass or orichalcum, that was the name of a kind of brass alloy during Roman era, the spread during Roman era. And so if they use orichalcum instead of standard copper as a source of copper for the production of Egyptian blue, they can avoid the use of natural, that at that time was difficult to find. However, we found only this occurrence of Egyptian blue with zinc. There is probably another in Turkey, but very few other. And so our idea is that there was a kind of invention of some workshop that stay open just for a while and then disappeared again. So that seems the end of Egyptian blue, but instead, no. From 2011 only, so it's just 15 years that we know that this is not the case. So Egyptian blue was still present in Italian Renaissance and only Italian Renaissance. It's not present in France or in Germany or in Greece or in the East Europe or in Northern Africa. No, only Italian Renaissance, as some very few authors. Now we have 11 painting. No, we have 8 painting known in the literature that are those one. That is the first one that has been discovered. Other 2 from Garofalo. Then there is those one that we discovered, and my colleague, especially Antonio Sgamellotti, found this one of Raphael in 2020, and we then go together also to further study on this famous painting by Raphael, The Triumph of Galatea. And then we discovered also the use by Raphael in Lodge of Cupid and Psyche, and then we discovered at the Louvre Museum one painting of Perugino, that is the master of Raphael. So it seems something that is related to a workshop in Italy that understood or how to produce or how to source Egyptian blue to be used in Renaissance. Is an ongoing discovery because we are working. There are some other paintings that probably will be soon published on those use of Egyptian blue during Renaissance. How they can have reinvented Egyptian blue during Renaissance may be thanks to Vitruvius, because the Treaty of Vitruvius was rediscovered exactly in that period in Renaissance. So maybe that is the key. We don't know exactly how and why. We know only that in Renaissance it was used only between the year 1500 and 1530, so the first 30 years of the 16th century. And then it disappeared again until the 19th century. So 300 of years without Egyptian blue. And then scientists in the 19th century, in full Egyptomania mood, because there was Napoleon in Egypt, the conquest of Egypt by Napoleon. So scientists going with Napoleon start to study again Egyptian blue, and then other scientists, and then other and other. And in the second half of the 19th century, finally they arrived to the production of a commercial Egyptian blue that was again available, and was available also during the 20th century. But during the 20th century, it was considered not so interesting. There were many other new blue pigment that have been developed during the 20th century and the 19th century that were more effective, more the painter were used to work with them, like ultramarine blue, cobalt blue, Russian blue that was of the 18th century too. Egyptian blue never get so popular. But at the very end of the 20th century, its property to be luminescent has been discovered and everything changed. But first to arrive there, we have to observe also that there are some cuisine of Egyptian blue that are Chinese blue and Chinese purple. They were discovered during the 20th century on archaeological object. So by American scientist Fitzhugh at the Smithsonian Museum, she found those first the Chinese blue, then the Chinese purple. Those two pigments, new pigments, similar. The Chinese blue is almost the same as Egyptian blue, but except that there is barium instead of calcium. The other one is a kind of byproduct. If you put not enough silica, you have Chinese purple. And so this is very interesting and made it possible to enlarge the family of Egyptian blue. You can also have hybrid of those material. Also the one with strontium, that is the element between barium and calcium. The structure that we observe, the synthesis, you can have a range of colors and a range of composition. And we invented, at this point, a new class of material that we can call Egyptian blue extended. It is ABX. It is very important to introduce because it's useful for the modern application. So those Chinese blue and Chinese purple were at the beginning were called Han blue and Han purple, but at a certain point they realized that they were widespread even before the Han Dynasty, and so now they are known as Chinese blue and Chinese purple. The interesting thing is that Chinese purple was the first to be developed and is present on the terracotta army, while Chinese blue is not present, is normally is used azurite, another blue pigment on terracotta army, and probably Chinese blue was developed as a byproduct of Chinese purple, so at the opposite as we can told. And so the production of Egyptian blue and Chinese blue are independent. So it's not something that arrived in China from Egypt 3,000 years later or 2,000 years later. It's something that has been developed by the beginning, starting by Chinese purple. That is the only purple inorganic pigment known. So probably they were interested on that pigment. Anyway, all those pigments are luminescent. Chinese blue, Chinese purple, Chinese and Egyptian blue. The one with the strontium instead of barium or calcium. All those ones are luminescent. Incredibly luminescent, and so incredibly interesting. Why they are luminescent is due to their structure, where copper is completely isolated. So when it gets excited by light, red light typically, but also green and also near infrared, it gets also difficult for it to be free from this energy. So it takes the energy and then how to give it back to the environment, since all those atoms are isolated and can give the energy to surrounding atoms. So the only way is to re-emit it, even if it is forbidden, this transition of this energy interaction. And so this luminescence is quite long, is long lasting, and so there is this relaxation of the energy from and those relaxation correspond to infrared light. So it takes a red light and it gives back infrared light. Since there is a kind of inner dispersion of energy, but limited, and then the final re-emission of energy in the infrared. And it is similar for Egyptian blue, Chinese blue, and Chinese purple, and so on. There is a little split anyway in the energy, exact energy, so we can have tunable production of infrared light, for instance, because Chinese blue is deeper in so is the infrared, so is maybe 1000 nanometer. Chinese blue, instead Egyptian blue is 920 normally. So we can play with the composition and tune the emission, and this is very interesting. Also, we can observe this with this camera that we have seen the image we have made on fresco, on sarcophagus, and so on. And we made also an improvement to these tools using a goggle. A goggle is a night vision goggle. Is a much more easy way to obtain this effect. Is cheap. Is balanced by inner algorithms inside the goggle, and allow you to observe it by the distance, even if there is some interference, and many other advantage. And with this technology, we invented this blue vision feature. So blue vision, a new way to see at object, and that can be a new field of like a virtual reality or augmented reality. We have also another tool that can be used, for instance, in museum to have an immersive experience, but also for many other reasons. In modern society, for instance, for device like self-driving or QR code identification, hidden QR code identification, and many other features like security inks for many other applications. All those specific features are even more interesting if we think that this material can be exfoliated. Salguero discovered this, and et al. Obviously discovered this in 2012, and from then there is a new field of exfoliation of Egyptian blue, so the nanotechnology of Egyptian blue that can allow to produce inks, for instance, that normally are forbidden for the dimension of the particles that are commonly observed for Egyptian blue pigment. So we can use ink, we can make textile with Egyptian blue, we can make fingerprint detection, many new advantage and new field that can exploit Egyptian blue features. One of them is bioimaging. Bioimaging is the ability to observe the inner body, and this group that is from Germany, that is Sebastian Cruz group, made a lot of step forward to use Egyptian blue as a new imaging method. That is impressive, really impressive, that in this new field of medicine. Also in medicine has been used by many scientists also in China in regenerative medicine, for instance. Also because it's very safe for the people and so is for the environment too. We will see it. Another field of modern technology that is very interesting for the exploitation of Egyptian blue is the production of energy. Specifically, there is one technology that is a luminescent solar concentrator technology that currently exploit the use of many materials like quantum dots that are based on cadmium, or perovskite that normally contain lead, and many other luminescent substances that obviously are maybe dangerous. Egyptian blue has a similar or maybe even more effective behavior and is a lot more safer of many of those materials. So if we exfoliate Egyptian blue and save the luminescent efficiency, that this is the challenge, then we can produce a luminescent solar concentrator based on Egyptian blue. We are working on that. There are many groups that are working on this target, this topic. Another interesting features of Egyptian blue is its antibacterial, osteogenic, and angiogenic features. There are many groups, especially in China, that are studying the osteogenic and angiogenic features. They made a regenerative medicine with those tools, also for dental, for instance, surgery, or for diabetes bound healing, and many other applications. There are about 30 papers about those new applications in medicine. And also we can try with anti-fouling material. That is another challenge. We know that ancient Roman used Egyptian blue, as especially Egyptian blue in bulk mosaics, where there are water in fountains, for instance, in Nymphaeum, where there is a lot of water. So and we know by literature that Egyptian blue has an anti-algal effect. So maybe the ancient already know this. Also, the medical factor was maybe known by the ancient. There are some recipes by Pliny, for instance, that state that the use of blue, grounded blue, for ulcers, and so to heal wound on like now we are trying to do again. So, but in those antibacterial and anti-algae effect is another opportunity that is linked to Egyptian blue. And we, in fact, in this in the Integrano project, we are exploiting those features, especially for tissue, that antibacterial tissue. This is our goal, and but they should be safe and sustainable by design. So this is our goal, to have safe and sustainable by design antibacterial material that are safer for the environment and for human in comparison to maybe silver or copper nanoparticles that have a similar behavior but are cytotoxic. Egyptian blue is not cytotoxic. This is the reason why it is so widely used in regenerative medicine. And so this is the opportunity for this exploitation. Another important thing to say is that Egyptian blue can be produced by waste, like rice husk, or so the shell around the rice, the single rice grain is made of those material that is organic but very rich in silica, nanosilica, natural nanosilica. And this is a vast, is a difficult to deal vast because it never get rotten because the presence of silica prevent it from decay, and so it stay in the environment for a very long time. And for this reason, it is incinerated. But what to do with the ash that is very rich in silica? We can do Egyptian blue, for instance, or we can also use fly ash from thermoelectric plants, for instance. Another silica-rich nano source that is a vast that we can use to produce Egyptian blue. And we can replace instead materials that are very dangerous, like cobalt blue, that is still widely used and is based on cobalt. Cobalt is an endangered critical raw material with a problem with extraction, ethical problem, price also problem, and many other problems. So we can try to optimize, to improve the production of Egyptian blue and to make it a viable alternative to cobalt blue, first of all, and to other blue pigments. And to tell all this history, we invented also an exhibition that is an exhibition that is it's not in a single place, but go all around Italy. We have had five steps in Italy in different cities. We have a kind of a trip of Italy. From the center, we go to the south, and then from the south, we are going back to the north, and we will finish in Turin, Egyptian Museum, and we will have this final step of this exhibition that starts in October of 2026. We involved 9 artists, Italian artists of different kind, different material. So only one painter, only one sculptor, only one mosaic, only one glass, and so on. And we invented entirely new material like plastic, Egyptian blue plastic, and many other to produce a work of art made with Egyptian blue that tell a story, that has a meaning, and also as a way to disseminate and to engage people into this new research. There are many other applications that we have no time to show in detail, like functional pigment phosphors. You can have a LED based on Egyptian blue. Security inks, microwave. There are microwave specific features, very interesting. Catalysis, energy saving is a cool pigment. Egyptian blue is a cool pigment. So where it get not hot when is in sunshine. It stay fresh, fresher than other blue pigments at least, and many other. Also, laser optical fiber fingerprint detection is already ongoing, so that are expected. So this is for the future. I thank you all for your attention. And I hope there is still some minute left for the question and answer.
Thank you so much, Marco. That was so fascinating. So I'd like to invite the audience. If you have a question, please leave it in the Q&A. In the meantime, I have a couple of questions to start us off. I'm really curious with all of these different variations of compounds that are similar but still very different. What's your definition for Egyptian blue? Bearing in mind these varieties that can exist, like the one that you mentioned that came from Italy during a time that natron was not. Oh, can you hear me okay? Is this okay?
I
Yeah?
can
Okay. Sorry,
I
the
can
thing was
answer.
frozen, so I wasn't sure. And okay. So yeah, bearing in mind the other variations of Egyptian blue that can exist, like the one that was made without natron that had a higher or the presence of zinc also, when you're analyzing objects, so either frescoes or actual statues. Is there a checklist of different techniques that you use to definitively say this is Egyptian blue versus any of these other varieties?
So to recognize that is Egyptian blue, now we have this wonderful technique that is visible induced luminescence imaging. So we observe if it is luminescent, basically. There are no other pigment that is luminescent with this, so because it's very rare, this feature. And so if we observe a painting with a visible light and record image in the infrared and there is a luminescence, then is for sure Egyptian blue. If the painting is ancient, because the only other pigment known that produce luminescence are the cadmium-based pigments that were developed during the 19th century. Okay, so if you are in the ancient world, so before the 19th century, if there is something luminescent in the infrared when there is only visible light present, that is Egyptian blue or Chinese blue or Chinese purple. There are no other possibilities. Then to observe which kind of Egyptian blue we are observing, we need to use other tools. We can start with X-ray fluorescence, but it's very dangerous in terms of you can have wrong conclusion because maybe there are some interference layer, the layer is thicker, the layer is thin, that can be interference by the background and many other things. So the best way is to take a sample, if possible, if you are allowed to, is to take a sample and observe it with some technique like ECM, and EDX, obviously, SEM EDX, so with microprobe, or Raman microscopy, and can give you a lot of information. If you want to go deeper, you can also check for isotopic composition, for instance, that has been done for the provenance or the trade route, recognized trade route, provenance workshop, and so on. So there are many features you can observe. Also, trace element is another idea that is sometimes used. So to go with the mix of materials. Obviously, all those features, almost all those features, stay in the glass matrix. So when you observe traditional Egyptian blue, we observe a glass matrix that is a kind of fingerprint with any kind of trace element in the raw materials. All of those things go into the glass matrix. Then there is the crystal of Egyptian blue, the crystal of cuprorivaite, so the calcium copper tetrasilicate, that are almost pure, virtually pure, that there can be sometimes, but it's very strange, substitution of strontium, for instance, for calcium. If I used a source of calcium that contains some strontium, that is normal. Not normally, many sources of calcium contain strontium. So you will observe at a certain extent the presence of strontium, but is very limited. Also, barium obviously can go into the matrix. Also, magnesium at a certain point can go into this into the structure of the single crystal. But the part that is very rich in information is the glass matrix that can allow you to understand this Egyptian blue was made, for instance, from bronze, because I found tin, for instance,
Yeah, that makes sense.
or many other information like this.
Okay, I'm going to go to the next question just in the interest of time. Thank you for your excellent presentation. Can you elaborate on the connection between Egyptian blue and Egyptian faience? Specifically, is it possible to know which technology emerged first?
Perfect question. I have a slide about it. I can
Yeah,
go.
perfect.
I didn't have the time to, because there are too many things to say. Oh, is Oh, this one. Okay, here we have faience and Egyptian blue comparison. Here we have two scarabs that are made of Egyptian blue, pure Egyptian blue. That is very impressive thing. But the net into the lower part of the image is made of faience. It's made of faience, and only a limited number of beds are made of Egyptian blue. So there are two different techniques, two different materials. They are somehow linked together because the raw material you use to make them are the same. But the specific material is different because the faience has a core that is sintered silica. So when you broke the faience, the inner part is not blue, it's white, because it's sintered silica covered by a coating that is a glass. So it's similar to the glass matrix of Egyptian blue. The coating of the sintered faience is similar to the glass matrix of Egyptian blue. So it's a copper-rich glass. But it is amorphous, is a vitreous material, is a proper vitreous material. Instead, Egyptian blue is crystalline, and if you broke one of those beds made of Egyptian blue, the core is not white, it's blue, because they are completely made of Egyptian blue. And it's a different technique, different technology, different material, even if are similar raw material.
Mm-hmm. Okay, and then the next one is, once per lecture, what do you mean by exfoliation, or what's the process? I guess this is for the 2D sheets that are.
So the exfoliation, okay.
Yeah.
Sorry, I didn't understand.
Oh, maybe just a quick one sentence answer for a follow-up.
Okay, sorry. No, exfoliation can be made in many different ways. The first one is hot water. The most common one is hot water, that was the one originally developed by Salguero. Then there is also surfactant ball milling that destroy the luminescence, and those are the most widely used.
Okay, just following up on the Egyptian blue and Egyptian faience, there's a question again from the person who asked it. Do you have an idea of which one emerged first? Is there any way to know which one came first?
Egyptian blue or faience?
Hmm.
This is a good idea, a good question. It's somehow accepted that faience was older, but it's not sure
Yeah.
idea. So the idea is that they start with ceramic technology, then they move to coating of, for instance, stone also. So they were able to make a coating, a glassy coating, a vitreous coating, like a glaze of a stone. Then they move to faience, that is similar to glaze. Then from faience, they move to Egyptian blue when you arrive to a certain ratio between the raw materials.
Okay, and we're over time, but there is still one more question. Hopefully this will be easy to answer. There's someone saying, thank you for a fascinating presentation. Do you recommend a specific brand of night vision goggles? And did you say that NVG have to be retrofitted to be able to view the Egyptian blue luminescence?
So there is a paper that has been shown here many times that I wrote on night vision goggles. In that paper, I use a trademark that is found on Amazon. So it's very, you can use any one that you want. It works. It works with any. And so maybe the most useful is the most cheap, probably. You need all. The important thing is that you have 4K resolution that I recommend. So high resolution. that is better for your image. And the possibility to take photo and videos that recommended. And that said, many are almost good. So now I'm going with a producer because many ask me for night vision Google modified, and so I go with a producer. Probably we will have a line in the future, but you can do it by yourself. You save a lot of money. So take a good one, not the cheap one, because the cheap one, but an average one is enough, and you will have beautiful photos and videos, and you can work even with some environmental light because goggles improve the quality of what you observe.
Okay, well, thank you so much. I think we're done now with questions. Uh, Please, let's thank Dr. Nicola one more time, and I hope to see you in the next webinar of the Material Science Pioneers in Art and Archaeology webinar series. It'll be in September, so next month there will not be a talk. And thank you again. See you.
Thank you all.
Okay, I'm gonna stop the recording.